Welcome back to part 2 of this video on topic 6.7 and 6.8. Today we're going to look at the fundamental theorem of calculus. Now we've already briefly touched on this a few topics ago. But we're going to get much more into the importance of it and how it's used right now. All right, it actually has two parts to it. The first part says the antiderivative of f. So we're trying to take the integral from a to b of f. If we take the antiderivative of f and we substitute in b and substitute in a and subtract them, that'll actually give us the area under the curve f. So what does that look like? Let's take a look at a basic example here for number 7a. This is something we can do without calculus. We can do this with geometry by now, but let's see how it works with calculus. If we take the antiderivative of 10, we would get 10x. And then what we do is we write a vertical line here and put our bounds at the end. Then the fundamental theorem says we substitute in b, so that would be 10 times 4. Subtracting, we substitute in a, so that's 10 times negative 2. And that would give us 40 plus 20, which is 60. Which again, we could have got that without doing all this work because the width would be 6 and the height would be 10. 6 times 10 is 60. But this is just illustrating a very basic case of the fundamental theorem of calculus. Part B. So the first thing I'm going to do is I'm going to rewrite my integrand as x squared plus x to the 1/2. And now I can take my antiderivative, which is x cubed over 3, plus x to the 3/2 over 3/2 from 0 to 1. Okay, I could simplify that if I want to, or I don't have to since I'm putting 1 and 0 in. If I put 1 in, I would get 1/3 plus 1 over 3/2. I'll simplify that in a little bit. Minus 0 plus 0, which is of course 0. All right, so my answer is 1/3 plus 1 over 3/2, which is 1/3 plus 2/3, or 1. Question C. So we're taking the integral from negative pi over 4 to positive pi over 4 of 2 secant squared theta d theta. So first of all, don't let the theta fool you. It's just another variable, that's all. So we're just taking a look at another variable besides x. Okay. And now what we're going to do here is we're going to take the antiderivative of 2 secant squared theta, which we know is 2 tangent theta, because the derivative of the tangent is secant squared. From negative pi over 4 to positive pi over 4. All right, if we substitute in, we get 2 tangent of pi over 4 minus 2 tangent of negative pi over 4. The tangent of pi over 4 is 1, so that's 2 times 1, minus the tangent of negative pi over 4 is negative 1, so 2 times negative 1. And we end up with 2 plus 2, which is 4. All right, letter D. So again, we talked about this last video. We can't take an antiderivative like this. There's no quotient rule for this. So I'm going to rewrite this as the integral from 4 to 9 of 1 over t to the 1/2 minus t to the 1/2 over t to the 1/2, which is going to be 1, but we'll get to that in a second, dt. And rewriting, I get the integral from 4 to 9 of t to the negative 1/2 minus 1 dt. So taking the antiderivative gives me t to the 1/2 over 1/2 minus t from 4 to 9. or if I want to rewrite that, it would be 2 root t minus t from 4 to 9. So it would be 2 root 9, or 2 times 3, minus 9, minus 2 root 4, or 2 times 2, minus 4. So that's 6 minus 9, which is negative 3, minus 4 minus 4, which is 0. So our integral is equal to negative 3. Number 5, the integral from 0 to natural log of 5 of e to the x dx. Well, that's just e to the x from 0 to ln 5. So it's e to the ln 5 minus e to the 0. E to the ln 5 is just 5. E to the 0 is 1. 5 minus 1 is 4. Okay, and our last one of these, the antiderivative of 3 over x would be 3 ln x, absolute value of x, from 1 to e squared. So we get 3 ln e squared minus 3 ln 1. You could drop the absolute value of ours since those are both positive. E squared and 1 are both positive. So this is 6 ln e minus 3 times ln of 1 is 0. Ln of e is 1, so I'm left with 6. So that's the first part of the fundamental theorem of calculus. The second part of the fundamental theorem of calculus, as we saw in earlier videos as well, says that if you have the derivative of an integral where the top bound is a variable, basically we just substitute that variable in to the equation, the integrand. However, if the top bound is a function of a variable besides just that variable, not only do you put that function in to the integrand, but you also have to multiply by the derivative of that function as well. Let's take a look at what that looks like in a couple problems here. It can be a little bit harder to understand until we actually see an example of it. So example A, 8a says evaluate the following. Derivative of an integral. The top bound is a variable. The bottom bound is a constant, so we can use this. Basically, all we're doing here is we're putting x in for t. That's it. Now, yes, we are multiplying by the derivative of x, which is 1, but we don't have to write that. It's just x squared plus 1. And if you went the long route, did this integrand, plugged x in, plugged 0 in, simplified, and then took the derivative, you would get back this same answer. Letter B, we see a constant here. We see a function of x here. Same thing. We are just going to put x right in for t. That's it. That's our answer. Part C, got a little problem here. The variable's in the lower bound now. Well, what we can do, and we learned this in topic 6.6, is we can take a negative outside of the integral to flip our bounds. And now we can take x and put it in for t. And our answer is just negative 4x. But as we saw in that yellow box there, if the variable is not just a variable, but instead it's a function of a variable, we have to multiply by the derivative of that using chain rule. All right, so for this one, we have derivative of an integral. Lower bound's a constant, upper bound's a function of x. So we take that function and put it in for t. So 5x squared plus 1. But then we also have to multiply by the derivative of 5x squared, which is 10x. So you can leave it like that if you want to simplify it to 50x cubed plus 10x. That's fine as well. One more practice problem with this. We see derivative of an integral. We see lower bound of a constant, upper bound of a function of x. So we can put that whole function in for t. and then multiply by that function's derivative, which would be 6x squared. Okay, no need to simplify it at all. If you wanted to, you would end up with this, 72x to the 8th plus 6x squared, but you can leave it just like that. The only reason why we would do this is if it's a multiple choice question. All right, that'll do it for topic 6, 7, 6, 8. Hope you enjoyed the video. Come back again next time.